What's up, y'all? Welcome back to another incredible quarantine video from the Mathnasium. Today, I'm going to be going over something I've been longing to teach. We're going to be talking about some transformations that we can make to data that looks a little weird. Prior to watching this video, I would recommend that you have reviewed content from Unit 3, which was bivariate data. I'll show you a cool website here to start us off. All right, this website is called gapminder.org. It's got a bunch of data about countries in the world. And right now, I am plotting the average income per person in the United States versus the life expectancy, or average income per person in the world versus life expectancy in the world, and life expectancy in the world, and each of the dots represents a different country, and the size is based off of their population. We're going off the center of the dot. So the United States, for example, has average annual income of 53,000 and a life expectancy of 78.8 years. So you can go through and check out other countries and see where they lie on those on this graph. As you can see, there's a trend that is, it's clearly curved. It's not a linear trend. So fitting a line of best fit to something like this is kind of a disaster. You'll also notice that if I click on income down here, I come down and it says I can display the x-axis as a linear or a logarithmic scale. Now, when we display it as a logarithmic scale, that looks pretty darn linear, doesn't it? So we're changing the scale of the x-axis, which is kind of putting things in the correct form. Now, fitting a line of best fit to this is much more reasonable. If you guys want to explore this website, I highly encourage you to do so. I also, coincidentally, something also follows a similar trend. I think I told you guys that I went on a diet back in February. So let's go ahead and take a look at that data. Here's me after my diet, looking pretty fit, looking pretty good. My diet is here, started beginning of February, ended roughly a month and a half later. I'm not going to tell you my weight now. That would be a little weird. But I will say that this is the after pic after I lost my weight. The before pic, what we have here has, this is a sketch artist's rendering. So it looks something along the lines of that. It was just drastic change over that time. Anyways, so over here I have the days after the diet began, and then I have my total weight loss since the diet began. So you can see that is definitely has, it looks like it's got some sort of a curve to the data. And you can see that there's variation from day to day, less variation down here, but I'm getting variation as I'm taking measurements on my weight. Things are causing that variation, like maybe I'm off based on my meals, or I wasn't being super consistent with how I eat or how much water I drank, so on and so forth. Okay, so let's go ahead and take a look. If we're looking at this data and we fit a line of best fit to this, the line of best fit that works for this data is as follows. Now, I have used the website Scatterplots to create this line of best fit. It says how many data points. This is the linear least squares regression line here, or least squares regression line for short. And if you look at the residual plot, if you're plotting these distances from the line here, and you graph that, you see a pattern where it seems like since it's curved, these points that are down low are down below the line here. So it's a low negative, positive, negative trend in our residual plot. And when you see a trend like that in a residual plot, it's usually a red flag that just a linear model is not necessarily what you want to go for. For example, remember r squared is the percentage of the variability that can be explained by our percentage of variability in y, basically, that can be explained by our model, and it's roughly 79.4%. So we can use this and we can make a prediction, but because we have this low, high, low model, if we're making a prediction, I'm asking to predict for 5 days. There's a chance we're not really sure where the line's going to lie at that point. We might be making an over approximation. We might be making. It looks like we're going to probably make. I would imagine it's going to be some sort of a little over approximation, but it'll actually be close. And if right here, if we were making a prediction for over here, it looks like the actual curve is something along this trend line here, and so. Oh, right here we're making right here we're making over approximations with our line. Right here we're making under approximations with our line, and right here we're making over approximations for our line, and we don't want to do that. We want to try and fit something better. So I'm going to try and pack all this into one lesson here. Let's go ahead and switch to black. And let's make our prediction. And this is old news, right? Predict how much weight Sligo lost after 5 days. Well, this right here, y hat, that is our predicted weight. And the way that we write that is with a hat. Hat rep means predicted. So I would do 2.40196 plus 0.2256 times 5, because x is in days, y is in weight. So I can come down here, do some math, and I'm going to pull up my, if you don't mind, I'm going to pull up my notes here. Perfect. So if you plug all this in and you simplify, you're going to multiply these two first, and you'll get roughly 3.53 pounds. So it's estimated with our linear, with our least squares regression line, that that I would have lost like 3.5 pounds in 5 days, which is, you know, it's decent, I think, for what we got going on if we had to fit a curve. But let's go ahead and take a look at some other models. It might be on for this spot here, but it might be off in a lot of other places. Let's take a look at some other ways we can do this. So here's the basic idea. We need to recall kind of these parent functions that you learned back in the day. And yes, you learned them for a reason. In statistics, when you see a curve like that, there are lots of different curves that maybe you are familiar with or that you've seen that we might be able to apply to our situation. So you can use basically anything and everything. It's fair game. So it's kind of crazy for me to try and go over everything in this situation. But the main ones we're going to focus on today, we're going to take a look at these two, the cube and the cubic and the cube root. So these two are mathematical inverses. They undo each other, right? And so you're going to need to remember what an inverse is. Basically that they undo each other. And so like those two are inverses. I could get another color here. Let's take a look at red. These two are inverses in red. Like a square root and a quadratic are inverses. You also have logarithms and exponentials are inverses. And yeah, there's lots of different things. And then the general shapes of like the reciprocal function, and you should be knowing that as well. So inverses are those things that undo each other. The way that you find an inverse operation, you know, you'll switch x and y and solve for the one, solve for y basically. But let's take a look at our data. So we have this curve to the data, and it would really be nice if we could take those data points and kind of, what we want them to be is we want this end to kind of shift over. We would like to do that. It might also be nice if we could take the beginning points and kind of shift them up a little bit and create a line in the middle. And it turns out we can kind of do that. We have to choose. So you could either try and choose a transformation that's going to move these points up, or maybe choose something that's going to move these higher points over. And that seems like it's cheating, but it's actually something that we can do. I'm going to go over how we do that. So we're going to go over the power transformations first and how you make predictions with power transformations. So the first one I'm going to look at is the square root. So what I did is I took all of the day data. That was just the days that I took my weight from after I started, and I took the square root of all of those values and I plotted them against the regular weight loss data. Now, what did that do? That kind of created this general, a much more linear pattern. So that square root kind of it took down some of those higher values and left these the same. It took away the basic shape. Basically, it scooted things over. Since we took the square root. And look at our residual plot. We kind of have a negative, positive, negative pattern, but it's not as drastic as the one that we were looking at before. We definitely have, it's a little more crazy over here. So let's go back and take a look at this one more time. Now this model, instead of explaining 74%, we're looking at explaining roughly 85. And the standard deviation of our residuals kind of shows how far away we can expect our predictions to fall. And on that data, that was 1.69, and on this one, it's 1.15. So our predictions for our weight loss are falling closer to our predicted line. And this is the same units. These are still in pounds, right? So a good indicator that this is a better model than the one that we chose before is looking at S and R. It's looking at the residual plot. It's looking at the general linear trend that we have. So I chose square root here. It's one way to do it. But what about the cube root? Let's take a look at the cube root. Is that any better? Well, the cube root has a lot of the same features of the same data. It makes things look really linear. It kind of makes our residual plot, I think, look a little nicer. It looks more randomly scattered about the line, less of an apparent pattern. Our R squared, the percentage of the variability it is explaining, and now technically this is supposed to be linear only, but it's a little bit higher of an R squared value and a little bit smaller of a standard deviation. So if I were to go with a model between the square root and the cube root, I would probably choose this model as the one that I would use. So I basically just went in and I took all the day values and I took the cube root of them and plotted them against the total weight. So I took the cube root of x, so to speak, of all the day values, the horizontal explanatory variable. Yeah, and we can do that. And we get this equation down here when we fit a line. Now, I didn't do anything different for fitting a line. I ran a least squares regression line on this data. So I took a regular old lin reg in my calculator, but I took the cube root of the x first. Okay, so what we end up here with is our y is still total weight lost. The x has changed. So this value right here isn't actually, this is actually y. This is not actually x. That x there is actually the cube root of x. So this is actually the cube root of x right there. So when we go to make a prediction, we have to be extra careful. We'll say, all right, the predicted weight lost, I should say, predicted weight loss total is negative 2.58. I'll say negative 2.584 plus 3.903, and I'll just say times the cube root of 5, because x is actually represented by the cube root of x. So when I'm coming in and doing my solving here, we get kind of a little bit extra step. We have to do this math. The cube root of 5 is, you get negative 2.584 plus 3.903, and the cube root of 5 is 1.71 about. Okay, so when we move down the line, we're going to end up getting roughly 4.09 pounds. So this model predicts that my predicted total weight loss is 4.09 pounds after 5 days. So that, I did not make a prediction here, but I did make a prediction here on the first one, and that said 3.53, so they're comparable. They're comparable. Maybe this one is, I said that line might be a little bit of an under approximation, it's hard to tell, but we'll never know because I never took a data point there, right? But we are estimating, and it's within our range of data values. So that's how you can do a cube root transformation. So, or a cube root transformation. Take the cube root x when you got that shape. I know what you're thinking. You're thinking, how do I decide what kind of transformation to do? Well, there are lots of them, and I'm only going to give you more. And I'm going to go over that kind of at the end. I'm going to show you what you can do. I'm going to show you how you make predictions, and then I'm going to show you how to decide. So here's another way we could change this data. So if I took this data, so what the square root does is you're taking all these x values, or the cube root, and you're shifting all these values over, which is kind of putting them in a tighter line. Okay, so when you take the cube root of a really small number, it doesn't get too much terribly smaller. When you take the cube root of a really big number, it's going to shrink by drastically. So these numbers are kind of sliding this direction. Well, it turns out we can also manipulate y. And we can actually, in this case, we won't be lifting here. We'll be taking these values and lifting them up to put them in line. And so we can do that with the extremes. Let's go back here. So we can actually take, and we're going to cube all of the y values. So this time I'm not manipulating x. X is the same. It's the number of days. And I'm cubing all of the y values. Now that also looks like it's much more of a linear trend. It looks like we have a random scattering of points. You'll notice my r squared is really, really bad. Well, that we don't really need to worry about, and we can't really compare this either. This could be a perfectly acceptable model. The issue is this is no longer y, this is y cubed. So we're going to get a lot more variability about the line, which can cause problems. But remember, when we're solving back, we're going to hopefully, basically because it's cubed, everything is becoming more extreme. So let's go ahead and make our prediction for y cubed. So our model is down here. X, this is days, just like it says at the top. But y hat is not y hat. It is y cubed hat, right? So this is weight cubed equals, and I'm going to do negative 14 point, I'm just going to round 48 plus 30.23 times 5, because that is just our normal day calculation. Now when we plug this in and we do our math, we end up getting equals 136.66. That is the weight cubed. So I'm actually gonna hold on, move that over a little bit, tidy this up just a smidge. Okay, that's our predicted cubic weight. So what we have to do is we now have to take the cube root of both sides to get our predicted weight, predicted total weight loss. So when we take the cube root of both sides, you'll get that the predicted weight is 5.15 pounds. Okay, so comparable, again, comparable to our guess. It looks like at 5, it's hard to tell where I'm at there necessarily on this chart, whether it's going to be an over approximation or an under approximation. We're fairly centered with this model, but it is a feasible model to make a prediction. Okay, let's go ahead and keep cruising. So you can use, we could cube y, we could cube root y. Those ones seem to work well. Cube root seemed to work really, really well here, and square root seemed to work pretty good too. Turns out you can also use logs, because if you're noticing a pattern here, the original data kind of looked like the shape of a cube root, and it kind of looked like the shape of a square root, and it kind of looks like a log. So let's go ahead and take a look at what happens when we do the log. Okay, I took the natural log of x days. So I took the natural logs of my explanatory variable here, and then I put my weight on the opposite side. So I didn't transform the weight. I just transformed the x days. Now look at now since this is y again, this is why we can actually compare our squared values here. So or rather s value. So s for this model, 1.023, is the lowest of the ones we've seen so far. So the natural log is looking like, it seems like I have a random scattering of points here and here. There's a big gap there where I probably should have taken more data, but that's okay. It's looking like we could possibly make a prediction. And it looks like this is going to be a good model for us to use. So took the natural log of x. Let's go ahead and do some math to make our prediction for 5 days. So if we're using this model to make our prediction, remember I took the y is actually the weight, so that is y. This x is actually the natural log of x. So when I plug that in over here, I'm gonna replace that. So our predicted weight is equal to 0.4066 plus 2.6915 times the ln of 5. Okay, that is our equation that we're using. So to get our predicted weight, we just got to simplify down and see what this boils down to. So when we do that, we get our predicted weight equals 0.4066 plus 4.3318. Our predicted weight is 4.7384 pounds. Okay, so that is also comparable to our predictions from the other models. So yeah, we've got a lot of thinking to do here, and we need to come up with a reasonable. If they give you a question like this on the AP exam, I think what they would probably do is maybe give you 2 models, or they'd give you a recommended transformation and expect you to be able to make predictions something along those lines. And again, what this S means is it means that our predicted weight is going to basically fall usually, or the actual weight is going to fall usually around 1.023 standard deviations away from the predicted value. Okay, so yeah, that's pretty cool. I think this is awesome. It's a cool way to make our data work. This is probably the most mathy lesson we've had all year. So how do we decide which transformation is best? I'm going to give you 4 tactics for doing that. Look for the linear trend. Say sometimes when you do a transformation, you don't end up getting a linear trend. That's a red flag that if you do that, you probably either need to do something else in addition or undo what you just did. So look for the linear trend. Think about the situation at hand. So think about like anything like let's just say the length of the fish versus weight is the one I have here. You're taking a measurement on the length of the fish, but when a fish grows, it's not just growing linearly. It's growing linearly as well as it's growing wide and it's growing tall. So it's growing in 3 dimensions, but you're taking a guess at using the fish's length as a guess. It turns out It's the same as like calculating volume. Weight is like representative of how much volume you have for that fish. So actually, a cubic model is what biologists use for the predictions for the length of fish. Cubic models are what are recommended. So think about the situation and make sure that it makes sense. Like, for example, a linear trend for my weight loss doesn't make sense because you're not going to just continue shriveling away. The more weight you lose, the harder it is to lose additional weight. So think about what makes sense for the situation. Number 3, look at the random scattering of points in the residual plot. You want to have that random scattering of points, and sometimes a line will look really, 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 really close to linear, and it's not. You have some sort of a pattern going on, so you need to be really, really careful with that. Check out that residual plot. Compare r squared and the s values. This only works basically if the y data between the two axes is in the same units. So if they're both in the natural log of y, you're fine to kind of look at these and compare models. But you cannot compare a model where you can't compare r and s in a model where one you took the natural log and one you did not. So look at those as a guide, but it's really taking all of this into account to make a judgment call. And this is something that takes practice and conversation with your colleagues a lot of the time. So how do you choose one? How do you even start to choose one? Because there are a lot of options. And this strategy is not always perfect. It doesn't always work. There's no priority here, really. But if a scatterplot appears to have the shape of some function f of x, so let's say, for example, when I was looking at the shape of my curve, it kind of looked like it could be a cube root, or it looked like it could be a square root, or it looked like it could have been shaped like a logarithm. So typically, what you do then is you'll take one of those functions, one of the parent functions, cube root, square root, fourth root, whatever. Choose one, and you're going to do that to all of your x data. That's one strategy that works. Another thing that you can do to transform data is take the inverse of that f function and do that to the y data. That will also can potentially give you a model that might work really, really well. I'll tell you what I mean here in just a minute. Okay, first, this is a lot here. Certain data may require transformations of both variables. So here I have one that it looks like it's growing kind of exponentially. Here it could be exponential. It could be like a power, like x squared or something. It's kind of hard to tell, but it kind of looks exponential to me. So what I did is I took the remember I could take all the data points and apply the parent function like e to the x. That would be something that would be plausible for you to do. Or another thing that you could do is take the inverse of y. The inverse of exponential is log. So since they're inverses, I took the log of y, and when I took the log of y, I got this shape. Well, shoot, that's starting to look like the data is logarithmic now. So then what you can do is take the log of x. So some data, when you take the first transformation, it doesn't end up looking super linear. So there's just x versus y, there's log y versus x, and there's log y versus log x, and that looks extremely linear. That's looking unreal, right? Really, 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 really good. Now this data is data I just made up for this example, but there's kind of there's no one you always do this. You have to do a little experimenting when you're choosing the model to use, I guess is what I'm trying to say. So you can kind of experiment and you can manipulate one variable or you can manipulate two. So how would I do the math and make a prediction? Well, I took the natural log of days and I took the natural log of my weight. This model is not great. It's not great as far as explaining variability, but when I did that, I ended up with this regression. Y hat, when I plugged it in, equals negative 0.0008 plus 0.669008x. But remember, when I plugged the data in, y hat is actually the predicted natural log. You're predicting the natural log of the weight. Okay. Minus 0.008 plus 0.669008, and that's the ln of days. Well, how many days? 5. So you plug in 5, you simplify this down, and you end up getting, when you do all this math, you end up getting that the predicted natural log of our weight is equal to 1.07593. And then when you get, that is not the predicted weight loss. That's the natural log of the predicted weight loss. So what I have to do to undo the natural log is raise that e to the power of 1.07593. So my predicted weight is equal to e to the 1.07593. So this model predicts that I actually lost. My predicted weight loss is 2.9327 pounds. Okay, all of them are basically between 3 and 5 pounds. All right, so hopefully that kind of strategy made sense with looking at a function and making your prediction. How am I expecting you to do this if this arises on the exam? They're probably going to give you the transformation that you need to do in order to make your predictions. What you can do, so I'm going to show you what I do to transform. I've got data in here, and basically here's my weight data. If I want to do, for example, the natural log of, or if I wanted to do graph the logarithm of this, and maybe I didn't want to use natural log, maybe I just wanted to use log base 10. So this looks like it's shaped like a logarithm, so I can take the logarithm of days. So here's days is, I've got all these over here. I tried lots of different things. So here's the log base 10 of days. I've got that data. And how you would do that on your calculator is you would create a list. One list is going to have days. One list is going to have the weight lost. And then you can then create new lists with the manipulated data. So maybe in list 1 you have days, list 2 you have weight lost, and then over in list 3 you'll say list 3 is equal to the log base 10 of list 1. Now be careful, I had to drop that first point because the natural log of 0 is undefined. Basically what you're, or rather it doesn't exist. So basically what you're doing here is plotting this data. This is the log of the x data. And so the log of days, log base 10 of days. So if you want to take that to Scatterplots.com, you can. You could type it into a Google Sheet. This is what I'm doing. I go to my explanatory variable and type, log days. You wouldn't even have to do this during the exam if you wanted to save time. And then that's the log base 10. And then over here, I have the total weight after the diet began. That's going in my response. That's weight lost in pounds. When you graph them, there you get your line or your scatter plot looking fairly linear. There's your correlation coefficient. Calculate the least squares regression line. It gives you your residual plot, and it gives you your equation here to predict. But that's actually natural log of x down there. So there's one way to do it on your calculator. Basically, you just store the log data in one list, and then you run a linear regression with the logged list in your in your explanatory slot. Okay, so let's do some quick examples of what data might look like and kind of some strategies for how you might try and straighten that data out. Oops, try that again. All right, so let's say you're given data that looks like this. So the general rule of thumb, if you have data that looks like that, you got a couple options. I'm going to tell you, if you got data that looks like that, your best option is probably what I would try first on the AP exam. I would be taking the log of x because it's exponential, and I would also take the log of y, or the natural log. Log base 10 or natural log, it doesn't actually matter. So that could be, I'd put a comma there. I'm going to say and. So you take the natural log of x and take the natural log of y, or you could do, or the log base 10, or you could do the natural log of x and the natural log of y. It doesn't actually matter. Those are two options to straighten that data out. Another thing that you might try is you might try taking x and squaring that. If you're squaring that x data, these ones get pushed over to the right, which is going to straighten out what you've got going on. They all get pushed to the right, but those ones get pushed more, basically. You could try x cubed, so on and so forth. To straighten that out, you could also try e to the x, or like 3 to the x, or some other number to the x power. So you would take all the numbers that, like, basically all of your x data is going to be in the exponent. Let's see here. And then you could also try, just taking the log of y and see how that works for you. I'm going to tell you this is the first one that I would try, or that one. All right, let's try another color here. Switch it up. All right, if it looks like this, okay, if it looks like that, you probably have some sort. I would just do log x, or natural log x. Don't do log x and y. That would be the first thing that I try. I would also try the square root or the cube root. Would be a good place to start. And then I might try, since that looks like a logarithm, the inverse of logarithm is exponent, so I might try like e to the y, or remember, if it looks like a logarithm, take the inverse of the y variable, right? E to the y or 2 to the y or something like that, and that's going to probably correct it a little bit. All right, and the last one that I'm going to go over here, and I think we've been pretty comprehensive with how you'd make these predictions, but the last one is really data can have all sorts of different shapes, right? If it looks like this, you got a couple options. That looks like exponential decay to me, so you could try anything that's exponential. Logging x and y is usually a really good choice. And then you might also want to try like 1 over x, or 1 over x squared, or something along those lines. And this can continue and continue and continue. There's lots of options that you can go on. So hopefully this has been helpful. Another option there, since this is the reciprocal function, 1 over y, is also a possible transformation there. Okay, anyways, yeah, so that's those are your options for transformations. That's all I've got for you for this video. Hopefully you guys learned something. So it's important to note here that with this strategy, we're not forcing a model to fit the data. We're manipulating the data, and there's a difference. So like if you go to like Desmos, or if you go to Excel and create and you force basically a quadratic to fit your data, you're not doing what we're doing. That is something else entirely. What we're doing is we're manipulating the data and then trying to get a line to go through it, basically. We're still doing linear regression, but moving stuff around a little bit. Hope you guys enjoyed the video, and we're gonna push ahead with more review videos after this. I'm getting pretty excited, and we're getting close to the end of the year. So thanks for watching, and we'll see you next time.